So dear students, let us to continue the electric potential. So in previous class we have already discussed about electric potential due to a single charge, that is V equal to 1 upon 4 pi epsilon naught Q divided by R, where R is the distance from charge to that point and Q is the charge of the source charge. Okay, and it is a scalar quantity. And electric potential due to number of charges is just the algebraic sum of the individual potentials at that point. So today we have to discuss about electric potential due to an electric dipole. All of you know about electric dipole. This electric dipole is consisting of two charges having same value but opposite in polarity. So two equal and unlike charges separated by a small distance. Okay. So we have already calculated the electric field due to an electric dipole. But today we have to discuss electric potential due to an electric dipole. So what is this axial line and equatorial plane or equatorial line? All of you studied. So let us to discuss the electric potential due to an electric dipole. So first one is at a point on the axial line. Axial line means the line which passes through both of the charges. See, here one charge you can take minus q, another charge plus q, and their separation is 2a, and this one is the direction of dipole moment, that p indicates the direction of dipole moment, O is the center of both the charges, means O is the midpoint of the line joining between two charges. So that point O is equidistant from Q and minus Q. Let the distance is A, and distance between two charges is 2a clearly. Let P be the point which is at a distance R from the midpoint of the line joining between two charges. Okay, so now here we are getting two potentials. Electric potential due to charge plus q, that is the charge which is placed at B. Now you have to use the same relation, V equal to 1 upon 4 pi epsilon naught Q divided by distance, but here the distance is R minus A. And similarly the electric potential at P due to another charge, that is minus Q, which is placed at A, is 1 upon 4 pi epsilon naught minus Q, because the charge is minus Q and the distance is R plus A. Is it clear how in these two cases the distances are R minus A and R plus A, and the charge is positive, we are getting the positive potential. If the charge is negative, we are getting the negative potential. Okay, and electric potential is a scalar quantity, so the net potential means simply you have to add these two. Okay, so now by adding these two, Q divided by 4 pi epsilon naught is common, take it outside. So we can write inside the bracket as 1 upon R minus A minus 1 upon R plus A. And by taking LCM and simplifying, we will get 1 upon 4 pi epsilon naught Q into 2A. R minus A into R plus A is R square minus A square. So Q into 2A is dipole moment, all of you know. So this is the final expression we are getting electric potential due to an electric dipole as 1 upon 4 pi epsilon naught P divided by r square minus a square. So note that if a is very very small, means the distance is, if P is far away from O, so then r square minus a square is simply r square. So we can write the electric potential is 1 upon 4 pi epsilon naught P divided by r square. So this is the final expression of electric potential due to an electric dipole. Is it clear? Okay. So now case 2, electric potential at a point on the equatorial line or equatorial plane. Okay, see, same charges q minus q separated by distance to a. O is the midpoint of the line joining between two charges. So just you have to draw one line which passes through O and perpendicular to AB. That one is the equatorial line. Okay, this one is the equatorial line. That line OC is there, no? So that one is the equatorial line. So now our aim is to measure electric potential at C. That C point is on the equatorial line. Okay, so now here electric potential at C due to positive charge is 1 upon 4 pi epsilon naught divided by BC. Similarly, electric potential due to negative charge is 1 upon 4 pi epsilon naught minus q divided by AC. And remember, the point on the equatorial line is equidistant from either charges. So means the distance from minus q to that point is same as plus q to that point. That is AC equal to BC. And just the net potential means simply by adding these two, 1 upon 4 pi epsilon naught is common, even AC equal to BC. So we get the electric potential is 0. So you can take anywhere, the point anywhere on the equatorial line, we are getting the potential is 0. Okay, is it clear? So note this, go to next, equipotential surfaces. So the term itself is equipotential surface. Equipotential surface means the surfaces having equal potential values. A surface at every point of which the potential due to charge distribution is the same is called equipotential surface. Okay, see, for a uniform electric field, this one is the uniform electric field, the field is uniform. See, you can take different planes, the potential on each plane is same. The potential on each plane is same. So whatever may be the potential on the first seat, it is same anywhere on that seat. Similarly, for second surface, you can measure the potential anywhere on the surface which is same. Let that potential is V2. By taking any point on the second surface we are getting V2 only. Similarly, this third surface also equipotential surface. Second one, for an isolated charge C, the spherical surfaces are equipotential surfaces for an isolated charge. Just you have to think, you take one point charge and just you have to imagine that point charge which is placed at the center of the sphere, and by measuring the potential on that sphere we are getting the same value, hence that spherical surface itself is equipotential surface. For example, if the radius of the sphere is r and the charge q is placed at the center of the sphere, then the potential on the sphere, on the surface of the sphere is 1 upon 4 pi epsilon naught q divided by r, which is same anywhere on that surface. So hence it is equipotential surface. You can take different spheres. Okay. For different spheres, the potential is different, but by taking any one of the sphere, whatever may be the potential which is same on that surface, that one is the equipotential surface. Okay. See some properties of equipotential surface. So no work is done in moving a test charge from one point to another on an equipotential surface. See, potential is same means no potential difference. If no potential difference means no work is done. How to measure the work done means potential difference into charge. ನೀವು ಯಾವ ಚಾರ್ಜನ್ನು ಮೂವ್ ಮಾಡ್ತಾ ಇದ್ದೀರಲ್ಲ ಒಂದು ಪಾಯಿಂಟ್ನಿಂದ ಇನ್ನೊಂದು ಪಾಯಿಂಟಿಗೆ, you have to measure the potential at first point and potential at the second point, and their difference you have to calculate the difference, and if you multiply with the charge, which charge is moving on that 2 points, no, so that one is the work done. So here potential is same because the surface is equipotential surface, means by taking 2 points the potential is same, so that is V and V. So potential difference is 0, so work done is also 0. It is very important. Okay. Is it clear? Next, we have to discuss about electrostatic potential energy. Potential energy, stored energy. Okay, all of you know about gravitational potential energy. Gravitational potential energy due to gravitational field, same as electrostatic potential energy due to electrostatic field or simply electric field. If electric field is existing in that place, definitely electrostatic potential energy we are getting at that place. Okay. So energy is measured in terms of work done, hence the electrostatic potential energy, the work done in moving a charge q from infinity to a point in the field against the electric force is called electrostatic potential energy. Is it clear? So work done we can measure as potential into charge. Okay. So now in first case, electrostatic potential energy of two charges. See, you take two charges Q1 and Q2. Let the position of Q1 is R1, position of Q2 is R2. Then the distance between Q1 and Q2 is R2 minus R1. Okay. So now the potential energy of this system is 1 upon 4 pi epsilon naught Q1 Q2 divided by AB. AB is magnitude of R2 minus R1. How we'll get this expression means, simply remember, you take one charge Q1 and you take one point B. So at B we are getting the potential now. How much potential we are getting? The potential at B due to charge Q1 is 1 upon 4 pi epsilon naught Q1 divided by AB. Okay, that is V. And work done is Q into V. And here we are keeping the charge Q2 at B. So that is Q2 into V. So V we have already calculated. So by substituting this, so we can say 1 by 4 pi epsilon naught Q1 into Q2 divided by AB. Clear? And here R12 is AB. This is the potential energy due to two charges. Okay. In next class, we have to discuss the potential energy of three charges. Okay. Thank you.